Hello Internet, my name is Quinn and this is Blondihacks. I'm working on my A3 switcher locomotive this week. We're continuing on with the oil pump. We're going to make the drive mechanism that actually makes the little piston go up and down. It's a really cool little mechanism that's compressed into a very tiny space, so lots of interesting operations as a result of that. So let's go. You'll recall this hideous but still loved oil tank has the oil pump body inside of it, and if I can get my fat fingers in there, here is the oil pump piston. And we made this last time, but you may not have noticed that there's a little shoulder on the top of it, and that is what is going to be driving this piston. There's a scotch yoke that's going to be driving that. It's going to be made from bronze, and I found these chunks left over from the main bearing production in my bronze bin. They're still super glued together. I would like them to be unsuper glued. A little bit of percussive persuasion takes care of that. Conveniently, the sides of that scrap are already machined. However, I want the end to be machined as well. You'll see why in a second. So I'll set this up in the shaper and take a light skim cut off of that. This part is quite an intricate shape and it's very, very small. However, it is flat. All of those properties make it an excellent candidate for a soft soldered fixture plate. So this surface that I'm cutting now on the end of this bronze is going to be the lower reference surface of the part. It's going to be the final bottom surface of the part essentially, but I need it to be flat and machined so it'll sit on the fixture plate in a way that will make a valid reference. Speaking of which, I will bring in a chunk of brass now that will be the actual fixture plate. The top and bottom factory surfaces of it are sufficiently flat and parallel. However, I want to make the edges parallel. Because this part is so small, I'm not going to be able to use the edges of the part itself for reference and setup in the vise, so I want the fixture plate to do that job for me. Now I can lop a slice off the top of that bronze bar, and it'll thus have one machined surface on the bottom and a bandsaw cut on the top, but the machined surface will be soldered to the fixture plate, and I can start my machining from there. Let's get that going then. Over to the hearth. Got that brass plate that's been trued up around the edges, well, two of the edges anyway. I only need two references on it, and I'll get some soft solder flux on there. I really hate this stuff. It smells really bad. Then I've got a piece of soft solder that I've hammered flat, so it'll sit between those two parts in amongst all the flux there. This is just basic plumbing solder that you get at any hardware store. It melts at a nice low temperature, but it's very, very strong, and when you're done with it, you can reflow it very easily to remove the part. This is a classic fixturing method that model engineers have been using for decades. It's a very old technique. Once the solder starts flowing, I hold the part down with a pick and hold it there until the solder cools off again and resolidifies. That ensures that that machined surface that I put on the bottom is sitting flat and parallel with the fixture plate, and the layer of solder between them is as thin as possible. I find if I do this method, I get a layer of solder that's less than 1/1000th thick. You can clean all the flux gunk off of there with IPA, clean it up, make it nice for the next step. I'm going to set it up in the mill now, and I'm going to start by surfacing the top of it and bringing it down to overall thickness. Now in principle, these sides that will then be parallel top and bottom, because remember the bottom is machined and it's sitting parallel to the fixture plate, which is also machined. However, getting the thickness right can be a little bit tricky because we don't know for sure how thick that solder layer is. As you'll see in a second here, I'll be measuring the thickness of it with a depth micrometer. However, the measurement is going to be a little bit incorrect because I'm including the thickness of the solder. Now I know from experience with this technique that that layer is going to be 1/1000th or less if you hold it down with the pick while it cools. However, just to be safe, I'll make the part 5/1000ths over thickness from this measurement here, and then I'll file it down to final thickness after removing it from the fixture plate. Just to be extra cautious, make sure the part doesn't end up undersize on thickness. Another way to do this that works is to leave the part longer than the fixture plate on one side. Give yourself an overhang, and then you can measure the thickness of that overhang with a micrometer. Next, I'm going to side mill the front and back edges, and that's because when the piece is soldered on there, it's in some arbitrary orientation that isn't going to be parallel to the edges of the fixture plate, and I want them to be for reasons that you'll see shortly. So I take a skim cut until the front and back are fully cleaned up, then I know those edges are parallel to each other and parallel to the edges of the fixture plate. The reason I want to do that is because the first feature I need to make is actually the mounting hole for this scotch yoke that's on the edge. So I can set this up on the edge of the part now, so the parallel is sitting on the edge of the part, not the fixture plate, although it would be fine if it was on the fixture plate also, since they are parallel. But now I can edge find on the top edge of this part and translate down 1/2 of the final thickness of the part. Remember, the part is oversized right now on thickness, but I can edge find in and go into where the center line of it is going to be, and then I can drill and ream this mounting hole for the piston. You'll notice another hole over there. Don't worry about that. It's for performance reasons. Just shut up. Don't worry about it. It's fine. Don't look at it. I'll do a quick test fit with the piston to make sure I got a good fit there. This piston is going to be Loctited in, so this fit doesn't have to be super, super tight, just enough for some Loctite, and that looks like that's going to be great. Now, I can set it up this way again, and this is the reason that those edges had to be parallel, so that when I set it up back in this orientation, that hole is square to the mill. And that's why there's an extra hole in there, because the first time I did this, I realized my mistake and had to go back and start over. But anyway, now I can put a gauge pin in that square reference hole, and I can center up on the x-axis using an edge finder on that gauge pin, because the slot in the scotch yoke has to be correctly positioned on x relative to this mounting hole. And that's because the scotch yoke is offset in such a way that when the crank is turning in the scotch yoke, it's pushing down directly above the piston on the power stroke to make sure that it's got maximum power and there isn't going to be any weird deflections caused by misalignment of the crank pin and the forces on the scotch yoke and so on. It'll make sense intuitively when you see the final mechanism, but the offset of this slot from the piston mounting spot is very important. So to cut this slot, I pre-drilled the ends so that the end mill doesn't have to do a bunch of plunging work. I don't like to make end mills do that. And this is going to be a pretty tough cut, so I'll get in the flood coolant here, fire that up, and in we go with my least favorite tool. You know it. It's the 1/16 end mill. I really hate these tiny, tiny end mills. It's really hard to tell what they're doing by feel, and it's easy to break them if you're pushing them a little too hard. So I just run them real fast and feed real slow and take light cuts and cross my fingers a lot, and maybe when I'm done the end mill is still there, or maybe it's gone and I have to go get another one. Fortunately, this part is 1/8 of an inch thick, which is the exact total cutting depth of this end mill. A 2-to-1 ratio of diameter to flute length is typical on end mills, so it's difficult to get a 1/16 hole cut any deeper than 1/8, which is fortunate that that's exactly what we need in this case. Otherwise, we would have had to flip the part over and do some kind of flipping reference, and that would have been a lot more work. Now I can come back in with a larger end mill and cut the outer dimensions of the part, the final outer dimensions, relative to that slot. And this is essentially removing all the excess material. The starting block was plenty oversized so that I could put the tiny part somewhere in the middle and not have to worry too much about where the slot and the mounting hole ended up. And now I can cut the outer edges all the way down, all the way around to line up with that. Not counting the bottom edge. That bottom edge was a final surface. Everything was measured from that bottom edge, or what's the front edge in this mill setup. Here you can see another advantage of these soft solder fixture plates. The plate itself is sacrificial, so you can cut into it a little bit to form the final outline of the part. This part is also a really good example of where soft solder fixturing shines above superglue fixturing, which a lot of us do a lot of the time nowadays. We have superglue these days. However, superglue has a minimum part size where it will work, because as the size of the part goes down, the strength of the glue goes down by the square of the size, because it's surface area that we're talking about. However, the cutting forces don't change with the size of the part. So there is a moment where a part gets small enough that the superglue can no longer hold because there isn't enough surface area under the part. Soft solder, however, is orders of magnitude stronger, and I've never found a part that's too small for soft solder to hold. But I know for a fact superglue would never have survived in this situation. This part is way too small. Then when we're done, a little bit of heat breaks the part off of the fixture plate. There will be a thin film residue of solder on the back of it, but we can just file that off, and recall that I needed to file this part on the back anyway because I know it's going to be a little bit over thickness still. I make sure to file the back because the top surface was my reference for all of the features. So I'm only reducing the dimension from one side to bring it down to thickness, and that ends up with our piston mounting hole in the center as intended. One neat thing while doing this, right when I got to final dimension, this amazing little piece of swarf fell out of the slot. So this is the two pilot drill holes at the ends of the slot and then the bottom of where the milling cutter went for creating the slot. It's just a perfect little piece of scrap. In machining, even the swarf is beautiful. You gotta love it. That leaves us with this part, which is fully functional and on dimension all the way around. It's just missing the cosmetic details now. There's some angled slopes at the bottom, and the ends and corners are all rounded, so I'll lay that out and do this with some filing. This is, again, just cosmetic, so just do it by eye. I find that these small size Knipex parallel smooth jaw pliers make quite a good hand device for this type of work. Just gotta make sure the jaws are not gonna be touching the file when you're working. You don't wanna file the ends of your rather expensive Knipex pliers. And there is the final part. That was quite tricky, that thing, but it went really well. I was pretty proud of myself for coming up with an order of operations for something that small and that intricate. I guess I've actually learned something throughout this locomotive build about how to make parts like this. The piston fits in there, then it'll get Loctited in, as I said. It's looking good. All right, we can move on now to the next part of this assembly, which is going to be the crank that drives that Scotch yoke. This starts over on the lathe, as you might imagine, with steel. This happens to be 1144, but I don't think the alloy matters very much. Any mild steel would be fine. We're going to turn a little crank disc out of here, starting, of course, by facing off the end, as is tradition. You'll see me switch cutting tools when it comes to do the turning on this. That tangential tool, which I love, was for some reason not cutting well on this 1144. 1144 machines extremely easily. It's beautiful stuff, but for some reason that tool wasn't working. Might need a regrind, or tool post angle might have been wrong. I don't know. It was just quicker to switch tools and figure it out later. On to the center now. The drawing calls for this crank to be threaded, and that is unusual. With a crankshaft, you want two things to be true. You want the crank to be running very concentrically with the shaft, and you want the plane of the crank to be very square to the shaft. And guess what are two things that threads are real bad at? So here we're using the threads to hold the crank in place and relying on it to keep the crank coaxial and square to the drive shaft. And I gotta be honest, I don't love that. I think it's being done here for ease of assembly, and I guess concentricity and squareness aren't that critical here, so we can get away with using threads. But just to improve the odds of success a little bit, I'm going to do this. I have an extremely tiny watchmaker's boring bar that a viewer donated many years ago, and I'm going to use it to create a tiny counter bore outside of this thread. Now it happens to be a left-hand bar, so I'm cutting on the back of the part, running the lathe in reverse, but it's fine, it'll still work. What I'm going to do is cut a little counter bore, very shallow, just 20 thousandths, that is the diameter of the drive shaft. In principle, this will create a square and concentric registration for the drive shaft to seat into when the crank is threaded onto it. I mean, this probably isn't necessary because Kozo's designed it this way and many of these locomotives have been built and they're fine, but that just wasn't sitting well with me. I don't like seeing threads being used for things that threads aren't good at, but you can see the tiny little counter bore that I made there. I don't know, maybe it'll help. Who knows? On then to the mill, while it's still attached to the base stock and it's easy to hang on to, I'm going to center this up on the spindle and we're going to drill the crank pin hole with the offset specified in the drawing. This also would have been easy to do in the 4-jaw chuck on the lathe with an eccentric turning operation, but I already had the collet chuck in when I started this part, so I just kept going with that and switch over to the mill for this little part. That gets drilled with a number 53 drill, and I'll do a quick test fit to make sure that the shank of a number 53 drill is a good fit in there, which it is. More on that in a second. This is an interesting design choice that's been made there. All right, now we can take it back to the lathe and part this thing off to final thickness. I mean, I suppose you could have done this on the mill with a slitting saw as well, but slitting saws are awful, and parting things off on the lathe is much more pleasant. Plus you can chamfer the edges and do a nicer job of it. Slitting saws are a last resort sort of tool. They're never fun. Now about that drill. The drawing calls for the pin on this crank to be made of high-speed steel, which is a very interesting choice. It must need to be very strong indeed and very durable. So the drawings suggest making the pin by cutting the end off of a number 53 drill. And I happen to have a lot of number 53 drills lying around, so that was an easy choice. That is indeed what I will do. I use this size a lot, and they come in packs of 10, so I have a lot of them around, a lot of extras. So the one that was currently in my drill index probably was getting dull anyway, so I sacrificed that one, put a brand new one in the index, and made the pin out of that. And we'll come back to that pin in a second. But next I'm going to make the drive shaft. This is a very simple thing, precision ground rod. Put a E-clip groove in one end, face it to length, put a thread on the other end. And this is that thread that's going to go into the crank. But the other interesting thing here is that the thread is only about 2/3 of the depth of the thickness of the crank. And I'm not sure why that is, except maybe just to ensure that it doesn't poke through and cause interference on the scotch yoke. I'm not sure. But a lot seems to be riding on the exact depth of this thread. So I followed the dimensions, and I'm not going to question the drawings. Here we'll test fit here with the crank, making sure my counter bore is facing the shaft, so it'll hopefully seat on there, keep everything square and concentric. Or maybe that was a waste of time, who can say? It seems to go on there though, so I guess that's correct. Now I'll remove that part from the chuck and show it to the camera. Every time. You guys have no idea how much time I spend looking for parts that I've dropped because I was trying to hold it at a funny angle to show it to the camera. Yeah, well, luckily that one I did find and I didn't have to make it again. So there, see? Are you happy? You got to see the finished part. The things I do for you people. Okay, moving along. There's a brass kind of shouldered nut thing that goes through the back of the oil pump, and it has the bearing in it for this drive shaft. So there's two pieces to this, and I don't know, it's not a very interesting part, so I thought I'd do something different with the edit. Here's the entire making of that part. Start to finish, no edits other than being sped up. So if you're interested in all of the little shenanigans that usually get edited out when making a part, this is it. This whole part took 18 minutes, and I can only do this with a simple part because it's simple enough that it will fit within one recording file on my camera. So I don't know, trying something different. Is this interesting? I don't know. Jatsi. Here's those two parts, the little bearing nut thing, and that goes through the back and it gets clamped in place with this nut, and it gives the crank a bearing axially and presumably a thrust face on the end of it. In this moment I was thinking, careful not to drop that nut in the oil, and then I immediately dropped it in the oil, of course. Clean that off, try again. Okay, so I snug that guy down. There's a shoulder, as I said, on that bolt that registers in the back plate, and then the nut clamps down on top of it. Hopefully final assembly now on the other components. I'll Loctite the scotch yoke onto the end of the piston. Then the little piece of drill gets Loctited into the crank. I've left that oversized because I didn't know exactly how it was going to end up sitting in the crank. I've got it on my bench block to make it flush on the back, and then once the Loctite was cured and at full strength, I could measure the overall width of the entire crank and use a stone to shorten the pin until that overall dimension is correct. I know the width of the crank is correct, so if I measure the overall width and bring that down, then the length of the pin will be correct. And of course, this is high-speed steel, so I can't use a file or anything like that. It needs to be some sort of stone tool. In this case, I'm just using a hand stone because it's small. Exciting times. Let's get this assembled and see if it's going to work. Get the piston installed back down in the pump. And then the crank, I can kind of sneak in between those two. And this might be why this crank is threaded, because assembly might be very difficult otherwise. That all has to kind of go in at the same time. And then the drive shaft can be threaded in from the back. Now it's important to know this pump only runs in one direction. It's driven by a ratchet wheel. Well, moment of truth. Let's see if this thing pumps when driven from that shaft and how difficult that is to do, because if it's too stiff, it won't work. And yeah, look at that. It's working. The scotch yoke has a tendency to walk itself sideways a little bit, and I learned that if I push forward very slightly on the crank, then the face of the crank squares up the scotch yoke and acts as a thrust face for it. I think that's probably the design intent here, so I may have to put a little bit of a bronze shim behind that crank. For whatever reason, the thrust face of the crank may have ended up in not quite the right place. However, there are a lot more parts to build on the back of this assembly, and one of those parts may set the end float and position of this crank, so I'm going to leave it for now, but I can fix that later. I can also make the crank a little thicker, make a new one. We'll see how it goes. But let's get some oil in there and see if this thing can actually shift oil. Oh, look at that, like a champ. And honestly, there's basically zero resistance on this, so it's pumping oil extremely well with very, very little resistance, so it won't need a lot of power to drive it. And I'm really very impressed with how well that's working. Kozo says that he has run tests on this pump and it easily builds 200 psi, which is great because it is going to need to force oil into the cylinders against boiler pressure. You can see from the giant mess it made that it's certainly pumping lots of oil. That is really working well. I'm very pleased with that. Those parts all went great. Next up is the ratchet mechanism that drives that pump at a 40-to-1 ratio and only in the forward direction. We'll get started on that next time. And as I said, I'll shim and or adjust the end float and end position of this axle as needed to make sure that Scotch yoke is running well when we're done. But I don't want to start making changes like that until I know for sure what the rest of the pieces look like, how they all work out, and how all the parts in the final assembly are going to relate to each other. This was a really fun little mechanism to make. It's impressive how well it works and how smooth it is for how small it is. I'm feeling pretty good about the result, and I actually enjoyed making these parts quite a bit. So I hope you enjoyed watching me do it. Thanks for your support, thanks for watching, and thanks to my patrons for making all of this happen, and I will see you next time. Stay steamy. Ooh, am I bringing that back? Oh, I don't know if I should. Demonetized.